Imagine a world where the skies burn with acid rain, the air crushes with pressure 90 times heavier than Earth's, and the ground glows red-hot under a perpetual volcanic haze. This isn't a scene from a science fiction nightmare. It's Venus, our closest planetary neighbor, a place so hostile it's earned the chilling nickname Earth's evil twin. But beneath its hellish surface lies something even more unsettling, a treasure trove of mysteries that have left scientists scratching their heads for decades. From bizarre atmospheric phenomena to geological oddities that defy explanation, Venus is a cosmic riddle wrapped in a sulfuric shroud. And today, we're peeling back those toxic clouds to uncover 25 of its most jaw-dropping enigmas. Why does Venus spin backward, defying the rotation of every other planet in our solar system? What lurks in those towering, continent-sized vortices swirling at its poles? And how could a world so similar to Earth in size and composition become such a monstrous mirror image of our own planet? These aren't just scientific curiosities, they're clues to a deeper story about how planets live, die, and sometimes take a terrifying turn, so buckle up. We're diving into the unknown, where every discovery raises more questions than answers. From cryptic radar reflections that hint at colossal underground structures to the mind-bending possibility of metallic snowfall on its scorching mountains, Venus doesn't just challenge our understanding, it mocks it. By the time we're done, you'll see why this deceptively bright morning star is one of the most fascinating and unsettling places in our cosmic backyard. The truth, we've only begun to unravel its secrets, and what we've found so far will leave you utterly spellbound. Think about how Earth spins like a top, gracefully twirling from west to east in a smooth 24-hour cycle. Now picture Venus doing the exact opposite, lazily rolling backward in the slowest dance of any planet in our solar system. A single day here lasts longer than its entire year, dragging on for 243 Earth days while spinning clockwise, defying nearly every other world in our cosmic neighborhood. What could twist a planet into such a bizarre rhythm? Scientists have wrestled with this puzzle for decades, and the leading theory points to a cataclysmic past. Some believe a colossal impact, an ancient smash-up with another massive object, could have sent Venus into this backward spin. Imagine a collision so violent it flipped the planet's rotation entirely, leaving it spinning the wrong way like a broken record. But there's another twist. Venus's thick, suffocating atmosphere packed with sulfuric acid clouds might also play a role. The sheer weight of its toxic shroud, combined with the sun's gravitational tug, could have gradually slowed and even reversed its spin over billions of years. It's as if the planet got stuck in cosmic quicks and its rotation dragged down by invisible forces. Yet the weirdest part, no one can say for sure. Competing theories exist, from magnetic field interactions to gravitational dances with Earth itself, but none fully explain why Venus ended up so out of step with the rest of the solar system. Every clue we uncover only deepens the mystery, leaving us staring at this backward world, wondering what truly lurks in its violent past. One thing's certain, Venus doesn't play by the rules. And that's what makes its slow, defiant spin one of the most baffling enigmas in our celestial backyard. Venus wasn't always the scorching, bone-dry wasteland we see today. Billions of years ago, it might have been almost unrecognizable, a world shimmering with vast oceans, cradling liquid water just like Earth. But now, not a single drop remains. The surface is so parched it makes the driest deserts on our planet seem like tropical rainforests. So where did all that water go? The most terrifying answer lies in something called the runaway greenhouse effect. Picture this: Venus with its thick atmosphere of carbon dioxide, trapped heat like a blanket with no escape. Temperatures soared, oceans began to boil, and water vapor, a greenhouse gas itself, piled into the air, trapping even more heat. It became a vicious cycle. Hotter oceans meant more evaporation, which meant more heat, until the planet crossed a point of no return. The water molecules, broken apart by ultraviolet radiation, saw their hydrogen atoms stripped away by solar winds, lost to space forever. Earth flirted with this same disaster, but thanks to our planet's ability to lock away carbon in rocks and oceans, we avoided the apocalypse that consumed our twin. But here's the catch: this theory doesn't explain everything. If Venus once had oceans, why did every last trace vanish so completely? Earth held onto its water despite similar early conditions. Some scientists suspect Venus's lack of a magnetic field left it defenseless against the sun's wrath, accelerating the theft of its water. Others point to volcanic activity on a scale we can barely comprehend, burying any remnants under layers of lava or spewing them into the atmosphere. Then there's the eerie possibility that Venus never had stable oceans at all, that its water existed only briefly before the planet's hellish fate was sealed. The deeper we dig, the stranger it gets. Recent discoveries suggest tiny traces of water might still hide in Venus's atmosphere, trapped in its sulfuric acid clouds. Could there be secrets lurking in those toxic vapors, or is this just the last ghost of a drowned world? One thing's certain: Venus's missing water isn't just a planetary mystery. It's a warning, a glimpse of what happens when a climate spirals out of control, and a haunting reminder that Earth's balance is far more fragile than it seems. High above Venus's scorching surface, something impossible crackles through its thick yellow clouds, flashes of energy so intense they dwarf anything seen on Earth. These aren't ordinary lightning bolts. Some stretch for hundreds of miles, lasting 10 times longer than anything in our thunderstorms, flickering like ghostly giants in the toxic haze. Scientists first dismissed them as instrument errors until multiple spacecraft confirmed the truth. Venus doesn't just have lightning, it has something far stranger. The mystery begins with what we think we know. On Earth, lightning forms when ice crystals collide in storm clouds, creating electric charges. But Venus has no water, no ice, just sulfuric acid vapor swirling in its atmosphere. So how does it generate these colossal discharges? Some researchers argue it's true lightning, just born from a different recipe. Droplets of sulfuric acid smashing together, building charge in ways we barely understand. Others propose something wilder: exotic plasma phenomena, where charged particles create fleeting rivers of electricity without the familiar thunderclap. Then there's the Venera missions, throwing fuel on the fire. Soviet probes in the 1980s claimed to detect constant lightning, so frequent it sounded like radio static. But later missions, like Europe's Venus Express, found almost none. The contradiction stumped scientists. Were the Venera instruments fooled by Venus's corrosive atmosphere? Or had the planet's electrical fury quieted over decades? The plot thickens with recent discoveries. Some flashes appear below the clouds where no lightning should exist. Others pulse at altitudes so high they defy physics as we know it. Could these be signs of a hidden volcanic eruption, electrifying the air with ash? Or maybe something entirely new, a form of energy discharge unique to Venus's hellish chemistry. One thing's clear: this isn't just about sparks in the sky. Crack this puzzle and we might unlock secrets about how atmospheres evolve, why some worlds turn volatile, and whether Venus's past was ever peaceful. Every flicker in those acid clouds is a cosmic clue waiting to be deciphered. At the surface, Venus moves in slow motion, an ancient world trapped in a backward crawl. But look up, way up, and something impossible happens. The planet's upper atmosphere spins like a hurricane on overdrive, racing around Venus in just 4 Earth days. That's 60 times faster than the surface itself rotates, a phenomenon so bizarre scientists call it superrotation. Imagine Earth's jet streams, then multiply their speed by 20. Now picture that frenzy wrapping an entire planet, a tempest of acid clouds hurtling non-stop in a never-ending sprint. What could possibly fuel such madness? The leading suspect is something called thermal tides. Here's how it should work. Venus, lacking oceans to buffer its heat, bakes unevenly under the sun's glare. The side facing the star grows blisteringly hot, while the night side plunges into frigid darkness. This extreme Chinese letter CREATES colossal pressure differences driving planet-sized waves in the atmosphere. Like a cosmic engine, these thermal tides might transfer energy from the lower atmosphere to the upper layers, accelerating the clouds to mind-bending speeds. But there's a problem. Even the most sophisticated climate models can't fully replicate this system. Thermal tides might explain part of the chaos, but they don't account for the sheer violence of the winds or why the superrotation persists so consistently. Some researchers speculate hidden dynamics are at play, perhaps turbulence from Venus's volcanic plumes injecting energy into the atmosphere, or mysterious waves ricocheting between its day and night sides. Others wonder if the planet's lack of a magnetic field allows solar wind to tango with the upper clouds, adding an extra push. The real kicker, superrotation, isn't just a Venus quirk. Saturn's moon Titan has it too, hinting at a universal atmospheric puzzle we've barely begun to decode. Every probe sent to Venus, from Japan's Akatsuki to NASA's upcoming missions, peels back another layer of this enigma, only to reveal deeper questions. Why does the speed vary with altitude? How do these winds interact with the planet's volcanoes below? And could unlocking this mystery teach us about weather patterns on exoplanets light years away? One thing's certain, Venus's atmosphere isn't just fast. It's a fluid dynamics nightmare, a laboratory of extremes where the rules of physics get rewritten. And until we crack its code, this whirling dervish of acid and wind will keep defying everything we thought we knew about planetary skies. 75 miles above Venus's infernal surface, where temperatures should be scorching under the relentless solar glare, something defies all logic: a mysterious cold layer. This atmospheric anomaly chills to -170 degrees Fahrenheit, a stark contrast to the searing heat below and the warm upper clouds above. It's as if Venus tucked an invisible freezer into its sky, a phenomenon so unexpected it sends climate models back to the drawing board. The cold layer sits like a thin, icy sandwich between two violently contrasting realms. Below it, the lower atmosphere broils under temperatures hot enough to melt lead. Above, the upper clouds bask in warmth from sunlight absorbed by sulfuric acid particles. But here, in this strange middle ground, the rules of physics seem to break. Scientists first detected it when spacecraft measurements revealed a sudden temperature plunge, one that theories struggled to explain. What could possibly cool this slice of hellscape? One leading suspect is sulfur. Venus's atmosphere is packed with sulfur dioxide, a gas that, under the right conditions, might form exotic compounds capable of radiating heat away into space like a cosmic air conditioner. Some researchers suggest unknown sulfur-based molecules could be absorbing and re-emitting infrared radiation in ways we haven't yet identified, creating this unexpected cold pocket. But sulfur alone might not tell the whole story. Another theory points to gravity waves, not the ripples in space-time, but vast atmospheric surges generated when winds collide with Venus's mountainous terrain. These waves could propagate upward, cooling the air as they go, much like how a breeze chills your skin. Recent data from Japan's Akatsuki orbiter hints at these waves intersecting at just the right altitude to trigger the temperature drop. Yet no simulation perfectly replicates the layer's abrupt boundaries or its persistence. The real puzzle: this cold zone shouldn't exist at all. Standard climate models predict a smooth temperature gradient from surface to space, not this jarring dip. Its presence hints at gaps in our understanding of not just Venus, but planetary atmospheres everywhere. If we can crack this enigma, it might rewrite textbooks on how energy flows in alien skies. For now, that frigid stripe remains a cosmic contradiction, a cold shiver in the hottest place imaginable. At the very top of Venus, where the planet's hellish atmosphere converges, something monstrous whirls in the darkness, a shape-shifting vortex so vast it could swallow continents. This isn't just a storm, it's a churning, double-lobed maelstrom, stretching thousands of miles across, spinning with a violence that defies every expectation. Earth has polar vortices too, but ours are polite by comparison, predictable, seasonal swirls of cold air. Venus's version, a frenzied enigma, morphing from hourglass to figure 8 to spiraling eye with no warning, powered by forces we can't yet name. The sheer scale of this phenomenon boggles the mind. Picture two colossal hurricanes, each larger than the continental United States, dancing around each other at the pole like cosmic partners in a toxic waltz. Infrared images reveal its structure, a seething mass of sulfuric acid clouds radiating heat in eerie patterns, folding and unfolding like a living thing. Sometimes it fractures into multiple vortices, only to merge back together days later. Other times it vanishes entirely, leaving scientists scrambling to explain where the energy went. What keeps this atmospheric beast alive? On Earth, polar vortices draw power from temperature differences between the equator and poles, stabilized by our planet's rotation. Venus has no such balance. Its super-rotating atmosphere slams into the poles at hundreds of miles per hour, yet somehow, this chaotic collision fuels the vortex instead of tearing it apart. Some theories suggest thermal tides, the same forces behind the planet's supersonic winds, might be funneling energy upward, creating a self-sustaining feedback loop. Others propose something stranger, that the vortex feeds on volcanic gases belched from below, transforming chemical energy into violent motion. The darkest mystery lies in its heartbeat. Unlike Earth's vortices, which pulse with the seasons, Venus's dark whirl has no rhythm. It accelerates, stalls, and contorts without pattern, as if haunted by invisible hands. Japan's Akatsuki orbiter once watched it split into 3 separate storms, then reform seamlessly, a feat that should be impossible without dissipating. Could hidden waves in the atmosphere be orchestrating this chaos? Or is the vortex tapping into some deeper, unknown reservoir of energy beneath the clouds? Every answer only uncovers deeper questions. Why does this vortex appear at both poles, yet behave differently in each location? How does it survive the planet's relentless heat and pressure? And most unsettling of all, what would happen if Earth's polar vortices ever became this unstable? The dark whirl of Venus isn't just a curiosity. It's a window into how atmospheres can spiral into madness, and a reminder that even in our own solar system, nature still holds cards we've never seen. On Venus, where mountaintops should be as barren as the rest of its scorched landscape, something glimmers. Radar maps reveal an eerie phenomenon: high-altitude plateaus reflecting signals with a metallic sheen, as if dusted with snow. But this isn't water ice, it's something far stranger, a mysterious compound, possibly bismuth or lead sulfide, coating the peaks like frost forged in a demon's workshop. No such substance exists naturally on Earth's surface, so how did it get there, and what unnatural process could paint mountains with metal? The leading theory starts with volcanoes. Venus is a world littered with ancient lava flows and towering volcanic constructs, some rising higher than Everest. When these giants erupt, they might spew metallic vapors, elemental hitchhickers like bismuth or lead, into the lower atmosphere. As these gases rise, the planet's relentless heat and crushing pressure could force them to condense into crystalline particles at cooler, higher altitudes. Picture metallic fog settling on the peaks, clinging like glitter to the only terrain tall enough to catch it. But here's where the mystery deepens. If this is volcanic fallout, why does the snow appear only in patches? Earth's volcanoes distribute ash evenly. Venus's metallic dust seems to favor specific slopes and ridges. some researchers suggest electrostatic forces might be at play, charged particles drawn to high ground like iron filings to a magnet. Others propose an even wilder idea, that Venus's corrosive atmosphere chemically transforms surface minerals over time, leaving behind metallic residues as the original rock erodes away. Then there's the atmospheric angle. At those elevations, temperatures drop just enough for certain sulfides to stabilize. Lead sulfide, for instance, could form delicate crystalline structures, blooming like poisonous flowers in the thin, toxic air. But nothing in our solar system prepares us for this. Even Mars's carbon dioxide snow or Titan's methane rain can't compare. Venus's metallic frost exists in a category of its own, a surreal byproduct of chemistry gone haywire under conditions too extreme for earthly parallels. The implications are staggering. If this snow is actively forming, it means Venus's atmosphere is still a dynamic laboratory, brewing compounds we've never witnessed. And if it's ancient, preserved by the planet's lack of erosion, it could be a time capsule hinting at volcanic eruptions from eons ago. Every theory raises new questions. Why do some highlands gleam while others stay dark? Could these metals hint at undiscovered mineral veins beneath the surface? Or are we seeing the aftermath of some colossal, planet-wide chemical reaction lost to time? One thing's certain, this isn't just about shiny mountaintops. It's a clue to Venus's hidden geological heartbeat, a signpost pointing to processes we've yet to imagine. And until we land a rover on those deadly slopes, tasting the air and scraping samples from those glittering ridges, the truth will stay just out of reach, a metallic whisper on the winds of a world that refuses to be understood. For centuries, astronomers have documented something impossible flashing in Venus's toxic shroud. Sudden, unexplained bursts of brightness that ripple across its clouds like cosmic fireworks. These aren't subtle flickers. Some events have doubled the planet's reflectivity in mere days, lighting up its sulfuric haze with a brilliance visible from Earth since at least the 1600s. Galileo himself might have witnessed one, scratching his head at a world that seemed to flare without warning. Today, with all our technology, we still can't say for sure what's sparking these eerie illuminations, only that they hint at forces far wilder than we imagined. The leading suspect, volcanoes. Venus is littered with more volcanic structures than any other planet in the solar system, and if even a fraction are active, their eruptions could be hurling plumes of reflective ash high into the atmosphere. Imagine a volcanic burst so powerful it sprays sulfur dioxide crystals into the upper clouds, where sunlight bounces off them like a mirror. This would explain the burst's fleeting nature. The crystals would eventually clump together or sink, dimming Venus back to its usual pallid glow. But here's the catch: no telescope or probe has ever caught a Venusian volcano in the act. The planet's thick clouds veil everything, forcing scientists to play detective with indirect clues. Some point to spikes in sulfur dioxide levels, a gas that sunlight quickly breaks down, suggesting fresh volcanic injections. Others note strange thermal hotspots spotted by orbiters, where the ground seems suspiciously warm for a world that's supposedly geologically dead. Then there's the timing. Many brightening events coincide with solar storms, raising the unnerving possibility that the sun's fury might be triggering these outbursts by stirring Venus's atmosphere like a spoon in toxic soup. The weirdest twist: not all brightenings fit the volcanic script. Some unfold too fast, as if the clouds themselves are undergoing chemical reactions we've never seen. Laboratory experiments show that sulfuric acid droplets could suddenly crystallize under certain pressures, scattering light in dramatic ways, but Venus's atmosphere shouldn't hit those conditions naturally. Unless, of course, we're missing a fundamental piece of its chemistry. What if the answer lies in something even stranger? A handful of researchers float the idea of electrostatic discharges, planet-scale lightning charging the clouds into temporary brilliance. Others wonder if meteors slamming into Venus's dense air might vaporize into reflective dust, but these theories raise more questions than they answer. Why do the brightenings cluster in specific latitudes? Why do some last weeks while others vanish overnight? Every flash in those clouds is a taunt, a dare to understand a world that refuses to follow the rules. Until we peer beneath its veil, Venus will keep its secrets flaring when it pleases, daring us to explain the unexplainable. And with each mysterious pulse of light, it reminds us just how little we know about the planet next door. In 2020, a discovery rocked the scientific world, one so provocative it rekindled an age-old question: could life exist on Venus? Astronomers reported traces of phosphine gas floating in the planet's temperate cloud layers, a molecule so stubbornly linked to biological activity on Earth that its presence sparked immediate controversy. Here, in the most hostile environment imaginable, something was producing a gas that shouldn't exist in abundance without living organisms to create it. The implications were staggering. On Earth, phosphine is primarily manufactured by microbes thriving in oxygen-free environments like swamps or the guts of certain animals. It's not a compound that forms easily through ordinary geological or atmospheric processes, at least, not in the concentrations detected. When the team behind the discovery, led by Jane Greaves of Cardiff University, spotted its spectral fingerprint in Venus's clouds, the announcement sent shockwaves through the astronomy community. Could floating microbes sheltered in those temperate cloud droplets 50 kilometers above the scorching surface be the culprits? The notion wasn't entirely far-fetched. Some extremophiles on Earth survive in similarly acidic conditions, and Venus's upper clouds offer a rare pocket of habitability, relatively mild temperatures, liquid water droplets, albeit sulfuric acid, and protection from the worst of the solar radiation. But almost as soon as the excitement flared, skepticism followed. Critics pointed out that phosphine can form abiotically under extreme conditions, just not ones we'd expect on Venus. Lightning strikes, volcanic eruptions, or even meteorite impacts might produce trace amounts, but nothing close to the observed levels. Others questioned the data itself. Some follow-up studies failed to detect phosphine at all, suggesting the original signal might have been a misinterpretation, noise masquerading as a groundbreaking discovery. Then came the geochemical counterarguments. What if unknown reactions between Venus's sulfur-rich atmosphere and its surface minerals could generate phosphine in ways we haven't yet imagined? The planet's bizarre chemistry has already thrown curveballs from metallic snow to superrotating winds. Why not this? The debate rages on, unresolved. Subsequent observations have only deepened the mystery. Some teams confirm phosphine's presence, but in fluctuating amounts, as if its source is sporadic or hidden. Others propose exotic alternatives, perhaps solar radiation or high-energy particles zapping atmospheric phosphorus into unexpected forms. Meanwhile, the original researchers stand by their findings, insisting the signal is real and that no known non-biological process on Venus can explain it. What makes this enigma so electrifying isn't just the possibility of life. It's the reminder of how little we understand about Venus's hidden workings. If the phosphine is microbial in origin, it would rewrite the rules of where life can exist. If it's geological, it reveals a gap in our understanding of planetary chemistry. Either way, the answer lies shrouded in those toxic clouds, waiting for future missions to pierce the veil. Until then, the question lingers, haunting and profound. Is Venus quietly harboring life, or is it simply fooling us with chemistry we've yet to decode? One thing's certain: this isn't just about a gas. It's about how we define the boundaries of life itself. Venus should be pockmarked with scars, just like Mercury or the Moon, battered by eons of asteroid impact. Yet when scientists mapped its surface, they found something bizarre. Venus has craters, but far fewer than expected, and they're scattered in a pattern that makes no sense. Some regions look freshly erased, smooth as glass, while others cling to ancient scars like cosmic graffiti. Where did all the missing craters go? The leading theory points to a planetary facelift, a cataclysmic resurfacing event. Around 500 million years ago, Venus might have torn itself apart in a volcanic apocalypse. Imagine lava floods so vast they drowned entire continents, burying old craters under miles of molten rock. This global resurfacing would explain the eerie smoothness, like hitting a cosmic reset button on the planet's skin. Earth's tectonic plates recycle its surface slowly, but Venus, lacking plate tectonics, could have erupted all at once in a single planet-wide tantrum. But here's the hitch: the craters we do see aren't distributed randomly. They cluster in strangely uneven ways, as if something shielded parts of Venus while leaving others exposed. If resurfacing was global, why are some ancient craters still pristine? Some researchers argue for differential resurfacing, localized volcanic outbreaks that spared certain regions. Others propose a darker twist. Maybe Venus's crust is so weak that old craters gradually sink, swallowed by the planet's sluggish, molten mantle like quicksand. Then there's the atmospheric wildcard. Venus's thick air acts like a cosmic bouncer, burning up smaller meteors before they hit the ground. But that doesn't explain the scarcity of large craters, ones that should have punched through regardless. Could colossal lava flows have filled even those, or is something else erasing them? Radar images reveal ghostly, splotches, ringless depressions that might be craters half digested by volcanic activity, their outlines blurred like wet ink. The real mystery isn't just the missing craters, it's the timing. If Venus wiped itself clean 500 million years ago, why hasn't it collected more new scars since? Either we're misreading its geological clock, or the planet has a way of hiding its wounds we've yet to comprehend. Every crater, or lack thereof, is a silent witness to a planetary past more violent than we dare imagine. Until we land a probe that can date its rocks directly, Venus's surface will keep its secrets buried under layers of lava and lies. In the final moments before succumbing to Venus's crushing atmosphere, the Soviet Venera landers made a discovery that still haunts scientists: bursts of bizarre radio waves crackling up from the surface like cosmic Morse code. These weren't random static or spacecraft interference. The signals pulsed with eerie regularity, repeating every few minutes with a precision that defied natural explanations. No storm, no quake, no known geological process on Earth produces radio emissions like these. So what or who was broadcasting from the depths of that sulfuric hellscape? The most unsettling part: the signals vanished the moment the landers touched down. It was as if the planet itself went silent upon contact, guarding its secrets. Early theories pointed to lightning, except Venus's electrical discharges, when they occur, are chaotic and high altitude. These waves originated near the surface, pulsing from the rocks themselves. Some researchers speculated about piezoelectric effects, where certain minerals under extreme pressure generate electric charges. On Earth, quartz crystals can produce weak radio signals when squeezed, but Venus's environment is orders of magnitude more violent. Could its crust be laced with vast metallic deposits, vibrating like tuning forks under the planet's relentless heat and pressure? Then came the plasma hypothesis. Venus's lower atmosphere is so dense it behaves like a supercritical fluid, a state between gas and liquid where bizarre physics reigns. Charged particles or plasma might form in this soup, interacting with the surface to create radio noise. But no lab simulation has ever replicated the Venera signal's peculiar rhythm. Others proposed a darker idea, that the radio bursts are artifacts of a runaway greenhouse effect gone haywire, chemical reactions in the rocks themselves emitting energy as they decompose under the heat, like a planetary death rattle. Yet none of these theories fully explain why the signal stopped on landing. Did the landers crush their source, or was the phenomenon somehow tied to the atmosphere surface boundary, a fleeting interaction between hellish air and broiling rock? Decades later, with no follow-up missions to the surface, the mystery persists. The radio whispers of Venus remain one of the solar system's most haunting enigmas, a reminder that even as we map distant exoplanets, the planet next door still holds secrets that defy our understanding. Stretching across Venus's swirling yellow clouds like a cosmic scar, a colossal Y-shaped formation reappears with eerie regularity, a structure so vast it spans the entire planet. This isn't fleeting atmospheric turbulence, it's a near-perfect symmetry, a gargantuan weather pattern that locks into place for days before dissolving, only to reform weeks later as if on schedule. Scientists first spotted it in the 1960s, but decades later, no one can fully explain why this monstrous shape emerges, persists, and vanishes like clockwork in a sky that defies all earthly logic. The sheer scale of the phenomenon is staggering. Imagine a storm system wider than the Pacific Ocean, its arms stretching from equator to pole, perfectly balanced as though drawn by some celestial architect. Infrared images reveal its secret. This Y shape isn't just clouds, it's a violent collision of winds where the planet's supersonic atmospheric currents slam together, forcing gases upward in a towering wave that casts a shadow visible from space. On any other world, such chaos would be fleeting, yet on Venus, this chaos somehow organizes itself into a flawless, recurring pattern. The leading theory points to solar wind, the relentless stream of charged particles screaming from the sun. Venus, lacking Earth's protective magnetic field, takes the full brunt of this assault. Some researchers argue the solar wind might stir the upper atmosphere, triggering instabilities that snowball into the Y shape. But here's the flaw: solar wind is chaotic, yet the Y structure reappears with near mathematical precision. If solar wind sculpts it, why doesn't the shape warp or fracture under the sun's unpredictable fury? Then there's the Coriolis effect, the same force that twists Earth's hurricanes into spirals. On Venus, with its sluggish rotation, this effect should be weak. Yet the Y-shape's arms curve with a precision that suggests some hidden hand is guiding the chaos. Some models propose standing waves, atmospheric oscillations trapped between the planet's surface and its upper clouds, resonating like a tuning fork to create stable nodes where the Y forms. But simulations can't replicate the structure's crisp edges or its stubborn refusal to distort. The darkest twist: this might not even be a modern phenomenon. Historical records hint that astronomers as far back as the 17th century documented similar patterns in Venus's haze long before we understood its atmosphere. Could this be a permanent feature, cycling in and out of visibility as the clouds churn? Or is it a time bomb, a sign of some slow-motion atmospheric collapse we've yet to comprehend? Every probe sent to Venus stares at this formation, and every theory falls short. The Y shape mocks our understanding, a riddle written in acid and wind. Until we crack it, we're left with a chilling realization: even the most basic forces on Venus don't play by the rules. And if we can't explain a cloud pattern next door, how can we hope to understand the storms on worlds light years away? Deep beneath Venus's suffocating clouds, infrared eyes have spotted something that shouldn't exist: glowing fingerprints of heat scattered across its surface like embers in the dark. These aren't uniform radiation patterns expected from a slowly cooling world. They're concentrated hotspots, some burning hundreds of degrees hotter than their surroundings, clustered in bizarre patches that pulse unpredictably over time. For planetary scientists, these thermal anomalies aren't just curiosities, they're smoking guns. Venus might still be volcanically alive, its fires burning in secret under that toxic shroud. The evidence first surfaced in data from the European Space Agency's Venus Express orbiter. Its infrared spectrometer mapped the planet's surface heat through the clouds, revealing zones where the ground radiates far more energy than the rest of the scorched landscape. Some hotspots align with known volcanic structures, colossal mountains like Mont Mons, towering 5 miles above the plains. Others erupt in the middle of featureless plains with no visible geological explanation. The most unsettling part, these thermal spikes fluctuate. Some regions blaze intensely for months before fading, while others flicker on and off like a cosmic neon sign. This poses a devastating question. If Venus is truly volcanically active, why isn't the whole planet lighting up? Earth's volcanoes dot the edges of tectonic plates, but Venus has no plate tectonics. Its volcanism should be either planet-wide or extinct, not this patchwork of activity. Some researchers argue we're witnessing the death throes of a world. Perhaps magma chambers that once fed global eruptions are now isolated, sporadically bursting through the crust like geysers running dry. Others propose something far stranger, that Venus's thick crust acts like a pressure cooker lid, allowing heat to escape only where weaknesses formed eons ago. The smoking craters of Iron Mons tell an even darker story. This massive volcanic structure glows persistently in infrared, surrounded by lava flows that appear startlingly fresh in radar images, some possibly younger than a few thousand years. But here's the twist: the hotspot doesn't sit at the summit where you'd expect active vents. It clings to the mountain's flanks, as if something beneath is melting its way sideways through the rock. Could underground lava tubes be channeling heat like subterranean arteries? Or is this evidence of a new kind of volcanism, one where molten rock exploits cracks we've never seen on Earth? The debate splits the scientific community. Skeptics point out that without direct observation of flowing lava, these hotspots could have other explanations. Maybe metallic compounds in the soil conduct heat differently, creating phantom thermal signatures. Or perhaps the planet's runaway greenhouse effect is baking certain minerals to unnatural temperatures. But believers counter with a chilling fact: Venus has more volcanoes than any other world in the solar system, over 1,600 major structures. Statistically, at least a handful should still be awake. What no one can explain is the timing. Why do some regions flare up in sync, as if responding to some planetary scale trigger? Some suggest tidal forces from the Sun's gravity might flex Venus's crust, squeezing magma to the surface in pulses. Others whisper about volcanic lightning, electrical storms sparking above eruptions hidden by the perpetual clouds. The truth may lie in future missions like NASA Veritas Orbiter, designed to hunt for fresh lava flows with radar sharper than any blade. Until then, those glowing patches remain a paradox, a planet that refuses to die quietly, whispering its secrets in a language of heat we've only begun to decode. Whether they're the last gasp of a world or the birth pangs of something new, one thing's certain: Venus's fires are far from out, and that changes everything we thought we knew about how rocky planets age. Venus's surface hides a fleeting spectacle, ghostly streaks that materialize and vanish across its baked plains like cosmic chalk marks wiped clean by an unseen hand. These aren't static geological formations. Radar images from missions like NASA Magellan Orbiter reveal long, parallel grooves, some stretching hundreds of miles, that appear in one pass only to disappear in the next. They cluster in regions called wind stripes, where the planet's surface seems to rearrange itself with a randomness that defies explanation. At first glance, they resemble sand dunes sculpted by wind, but Venus's atmosphere is so thick near the surface that it behaves more like flowing water than air. Theoretically, such density could carve these patterns, except the stripes vanish too quickly. Wind-driven features on Earth or Mars persist for centuries. These come and go within years, sometimes months. Some researchers propose that volcanic ash, kicked up by eruptions, might temporarily settle into these formations before being redistributed. Yet orbital surveys show no fresh lava flows coinciding with the stripe's appearances, leaving the volcanic angle unproven. Then there's the electrostatic theory. Venus's scorching temperatures and acidic air could charge surface particles, causing them to levitate and align in eerie, temporary patterns. Laboratory experiments show that certain minerals, when heated to Venusian extremes, generate enough static electricity to make dust dance. but scaling this up to continent-sized streaks remains speculative. The darkest twist, some stripes reappear in the exact same locations after vanishing, as if the planet is etching and re-etching a cryptic message. No known process on any world behaves this way. Could underground seismic activity, Venus's equivalent of earthquakes, be vibrating the surface, sorting grains into transient designs? Or is this a symptom of something far stranger, like slow-motion chemical reactions transforming the terrain itself? Until a probe touches down to witness these disappearing acts firsthand, the stripes remain one of Venus's most unsettling riddles, a reminder that even its surface is anything but solid ground. Among Venus's endless geological oddities, few are as baffling as its pancake dome's mysterious, flat-topped volcanoes that look like they were pressed into the crust by a cosmic iron. These bizarre formations, sometimes stretching dozens of miles wide but rising no higher than a modest hill, defy every rule of terrestrial geology. On Earth, volcanoes are steep and conical, built layer by layer from flowing lava. But Venus's domes are squat, circular, and eerily hollow, their collapsed centers gaping like volcanic donuts. How does a world with gravity nearly as strong as ours produce structures that seem to float on the surface, their roofs too thin to withstand their own weight? The secret might lie in lava unlike anything we've seen. Earth's basalt flows are runny, spreading quickly into vast plains. But Venus's pancake domes suggest something thicker, a magma so sticky it oozes like cold honey, piling up in dense, sluggish mounds. Some scientists propose this lava could be loaded with silica, a mineral that turns molten rock into a viscous, tar-like fluid. Such magma wouldn't travel far. Instead, it would blob around the vent, inflating like a balloon until the pressure blows out the center, leaving behind a hollow shell. Picture squeezing toothpaste so thick it holds its shape, then poking a hole in the middle before it dries. Yet even this explanation raises eyebrows. Silica-rich magma usually signals explosive eruptions, like those at Mount St. Helens, but pancake domes show no debris fields or pyroclastic flows. Instead, their surroundings are eerily smooth, as if the lava simply gave up and froze in place. Another theory suggests an even wilder possibility, that Venus's extreme heat and pressure alter lava chemistry entirely, creating exotic compounds that behave unlike anything in Earth's playbook. At 900 degrees Fahrenheit and 90 times our atmospheric pressure, familiar rocks might melt into bizarre, high-density fluids that solidify into lightweight froth, structures strong enough to defy gravity, at least temporarily. The real enigma isn't just how these domes form, but how they endure. Radar scans reveal their roofs are paper-thin relative to their width, some barely a few hundred feet thick. Under Earth's gravity, such flimsy spans would crumple like tinfoil. Venus's dense atmosphere might act as a cushion, its pressure equalizing stresses. But even that can't fully explain why these fragile giants haven't collapsed under eons of tectonic strain. Unless, of course, they're younger than we think. Some researchers argue the dome's crisp edges and lack of erosion hint at recent activity, their hollow chambers still propped up by residual heat or gas pressure. Then there's the distribution puzzle. Pancake domes cluster in specific regions, often near volcanic rises called coronae, but never on Earth's seafloor or even Mars's vast plains. This selectivity suggests Venus's crust plays an active role, perhaps channeling magma through hidden weaknesses or chemically filtering lava types. Or maybe the domes are just the visible tip of something deeper, surface blisters atop massive magma chambers, their true scale hidden beneath the crust. Every unanswered question makes these formations more tantalizing. Are they relics of a forgotten volcanic era or signs of a world still geologically alive? Do their hollow cores hide underground caverns, or are they just scars from ancient explosions we've yet to understand? Until we sink a probe into one of these cryptic mounds, Venus's pancake domes will remain a delicious mystery, structures that shouldn't exist on a planet that refuses to follow the rules. Most planets shield themselves with powerful magnetic fields, generated by churning molten metal deep in their cores, but Venus plays by different rules. Despite being nearly Earth's twin in size and composition, its magnetic field is shockingly weak, a ghostly wisp compared to our planet's robust protective bubble. Even stranger, this field flickers unpredictably, surging and fading in ways that defy every model of how planetary magnetism should work. For scientists, Venus's magnetic enigma isn't just a curiosity. It's a glaring contradiction that threatens to upend our understanding of what makes a planet tick. The puzzle starts with Venus's core. Like Earth, it should have a molten iron heart spinning as the planet rotates, generating magnetism through the dynamo effect. But Venus rotates so slowly backward, no less that its core might not spin fast enough to sustain a traditional magnetic field. Some researchers argue the core could have cooled and solidified over time, shutting off the dynamo entirely. Yet here's the twist. Recent gravity measurements suggest the core is still at least partially molten. So why isn't it producing a stronger field? One controversial theory proposes that Venus's core might be layered like an onion, partly liquid, partly solid, creating a sluggish, unstable dynamo that sputters instead of hums. Then there's the atmosphere's bizarre role. Unlike Earth, where the magnetic field springs from the core alone, Venus's feeble magnetism seems tied to its hellish upper atmosphere. Solar wind slamming into the planet's ionosphere generates electric currents that induce a weak secondary magnetic field. This indirect field is flimsy, patchy, and constantly reshaped by the sun's fury, barely enough to deflect cosmic rays, let alone protect the surface. But this raises an even darker question. If Venus's atmosphere can create some magnetism, why can't its core? The two should work together, not exist in opposition. The real shock came when Europe's Venus Express orbiter detected sudden spikes in magnetic strength, bursts up to 50 times stronger than usual, lasting mere hours before vanishing. No known geological or solar event explains these surges. Some scientists suspect hidden volcanic plumes might be ejecting conductive material into the air, briefly supercharging the ionosphere. Others wonder if the planet's core, though weak, occasionally couples with the solar wind's energy, amplifying the field in fleeting outbursts. The implications are staggering. If Venus's core is still molten but inactive, it challenges the very definition of a planetary dynamo. If its atmosphere is the main magnetic source, it rewrites the rules for how planets shield themselves. And if those magnetic spikes hint at unseen underground forces, it means Venus's geology is far wilder than we imagined. This isn't just about magnetism, it's about how planets live, die, and sometimes defy the cosmos's expectations. And until we peer deeper into that toxic shroud, Venus will keep its secrets locked in a magnetic dance we've only begun to decipher. Venus might be the hottest planet in our solar system, but its nights hold an even deeper mystery, one that breaks the laws of physics as we know them. While temperatures on the sunlit side soar to a blistering 860 degrees Fahrenheit, the dark side should theoretically cool down under the endless night. Instead, infrared sensors have captured something impossible: sudden temperature spikes in the dead of Venusian night, where readings leap by over 100 degrees in mere hours. It's like opening an oven door to find the interior inexplicably hotter after turning off the heat, a violation of basic energy conservation that leaves scientists scrambling for answers. The leading suspect, a phenomenon called atmospheric gravity waves, not to be confused with the cosmic ripples of spacetime. On Earth, these waves occur when air masses collide over mountain ranges, creating invisible ripples that propagate upward, redistributing heat and momentum. Venus's version, however, is on a planetary scale. Its thick, sluggish lower atmosphere acts like a colossal fluid, with winds slamming into towering highlands like Aphrodite Terra. generating waves so powerful they could theoretically ferry heat from the day side to the night side like a conveyor belt. Some models suggest these waves might focus energy into narrow bands, creating localized infernos in the darkness like cosmic magnifying glasses concentrating sunlight onto ants. But here's where the theory collapses. Even the most generous calculations show these waves couldn't possibly account for the sheer violence of the temperature spikes. The energy required to heat vast swaths of the night side so abruptly would demand atmospheric currents beyond anything observed or even physically plausible. Worse, some surges occur far from any major highlands, in regions where gravity waves should be weak or non-existent. If atmospheric waves aren't the culprit, what unseen force is pumping heat into Venus's shadows? One radical hypothesis points to volcanic activity. If underground magma chambers are venting heat through fissures, they might supercharge localized patches of the lower atmosphere. But orbital radar shows no fresh lava flows corresponding to the spikes, and the heat signatures don't match the slow, steady release expected from geothermal sources. Another idea leans into Venus's peculiar chemistry. Metallic compounds in the soil reacting with sulfuric acid droplets in the air might trigger exothermic reactions, a planetary-scale version of chemical hand warmers. Yet lab experiments struggle to replicate the necessary energy output without catalysts that shouldn't exist naturally. The darkest possibility, we're witnessing the fallout of a runaway greenhouse effect gone berserk. Venus's atmosphere, already a thermal funhouse, might be trapping and recycling heat in ways no model predicts. Imagine the night side as a pressure cooker, where infrared radiation bounces between cloud layers instead of escaping, building to explosive crescendos before abruptly dissipating. If true, it would mean our understanding of planetary climates is fundamentally flawed, and Earth's own future could hold similar surprises. For now, these nocturnal firestorms remain one of Venus's most brazen riddles. Every probe sent to study them raises more questions. Why do some nights remain calm while others erupt? What invisible hand flips the switch on these thermal outbursts? Until we land sensors on that infernal surface, the truth will stay locked in the dark where Venus, defying every law of thermodynamics, keeps turning up the heat. Even in the eternal darkness of Venus's night side, some mountains refuse to fade into obscurity. Infrared scans reveal an impossible sight: entire highland ranges pulsing with an eerie glow, radiating heat signatures that outshine their surroundings by hundreds of degrees. These aren't volcanic hotspots or lava flows. They're cold, ancient rock formations that, by all accounts, should be as inert as graveyard stones. Yet something keeps them burning bright in the infrared spectrum, like cosmic embers that never cooled. The most baffling examples cluster around Maxwell Montes, Venus's tallest mountain range, where peaks tower 7 miles above the scorching plains. Day or night, these ridges emit a persistent thermal signature that makes them stick out like neon signs against the planet's otherwise uniform crust. At first glance, the glow might suggest lingering geothermal activity, except radar mapping shows no fresh lava or thermal vents in the area. The mountains are geological relics, possibly billions of years old, with no business radiating this much energy. One tantalizing theory points to mineral fluorescence. Certain metallic compounds, when exposed to Venus's corrosive atmosphere, might undergo chemical reactions that release stored energy as heat. Picture rocks laced with iron sulfides or exotic chlorides, slowly burning as they interact with sulfuric acid rain, a form of planetary-scale battery discharge. But lab tests struggle to replicate the intensity of these emissions. Even the most reactive Venusian analog minerals can't account for the sheer scale of the phenomenon. Then there's the residual heat angle. Venus's surface bakes under a runaway greenhouse effect, but that heat should distribute evenly, not cling stubbornly to specific peaks like a ghostly campfire. Some researchers speculate these mountains might be thermal sponges. their unique composition absorbing sunlight during the day and re-radiating it at night at an unnaturally slow rate. Yet even this falls short. The glow persists through Venus's months-long nights, far longer than any known material could retain such heat without an external energy source. The darkest twist comes from orbital gravity data. These glowing highlands coincide with regions where Venus's crust appears unnaturally dense, as if something massive lurks beneath them. Could underground magma chambers, long cooled but still rich in radioactive elements, be heating the rock from below? Or is there a more unsettling possibility that these mountains are taproots channeling heat from deep within Venus's mantle through hidden pathways we've yet to map? Every explanation raises new questions. Why don't all highlands glow, just these select few? What makes Maxwell Monty's burn brighter than the rest? And if this isn't geothermal or chemical, could it be something entirely new, a form of energy transfer we haven't discovered yet? Until we land a probe on those radiant slopes, Venus's shining mountains will keep their secrets, standing as silent sentinels in the dark, glowing with light no one can explain. Earth's atmosphere is nearly 80% nitrogen, a stable blanket that's endured for billions of years. Yet on Venus, our so-called twin, nitrogen is shockingly scarce, making up just 3.5% of its toxic shroud compared to Earth's overwhelming majority. This cosmic discrepancy isn't just a curiosity, it's a glaring clue that something catastrophic happened to Venus, something that robbed it of a gas so inert even our planet's most violent upheavals couldn't strip it away. So where did all that nitrogen go? The most obvious suspect is the solar wind, the relentless barrage of charged particles screaming from the sun. Without a magnetic field to deflect this assault, Venus's atmosphere lies utterly exposed, vulnerable to being slowly eroded away. Over eons, hydrogen and lighter gases would have been the first to vanish, ripped into space by the solar wind's fury. Nitrogen, being heavier, should have clung tighter, yet Venus lost almost all of it. The math simply doesn't add up. Even with billions of years of solar bombardment, models can't account for the sheer scale of nitrogen depletion. Something else had to have helped it disappear. One theory points to an ancient cataclysm, a collision so violent it blasted much of Venus's original atmosphere into space. Picture a protoplanet, one perhaps as massive as Mars, slamming into Venus in its youth. The impact wouldn't just knock the planet into its backward spin. It could have vaporized entire layers of air, scattering nitrogen into the void before the remaining gases collapsed into the crushing greenhouse we see today. But here's the catch. If such an impact occurred, why didn't Earth suffer the same fate? Both worlds formed in the same chaotic early solar system, yet only Venus ended up starved of nitrogen. Then there's the chemical angle. Venus's surface is a furnace, its rocks baking under temperatures hot enough to alter fundamental chemistry. Some researchers speculate that nitrogen, normally content to float harmlessly as a gas, might have bonded with other elements under extreme heat and pressure, forming compounds that sank into the crust. Imagine nitrogen locking itself away in minerals, buried beneath lava, flows like treasure in a planetary vault. On Earth, this process is negligible, but on Venus, where the surface simmers like a forge, it could have been a nitrogen death sentence. Yet even this explanation leaves gaps. If nitrogen was consumed by chemical reactions, why hasn't volcanic activity recycled some of it back into the air? Earth's volcanoes constantly replenish our atmosphere, but Venus's eruptions, if they still happen, seem to hoard their gases. Unless, of course, the nitrogen is trapped so deep that not even magma can free it. The darkest possibility, Venus never had much nitrogen to begin with. Its early atmosphere might have formed under different conditions, with chemistry that favored carbon dioxide over nitrogen from the start. If true, our twin isn't a cautionary tale of loss. It's evidence that small differences in a planet's infancy can echo for billions of years, turning two similar worlds into opposites. Every probe sent to Venus searches for answers in its thin nitrogen residue, tracing isotopes like breadcrumbs to the past. But for now, the mystery endures, a silent witness to forces we barely understand, and a reminder that even the most basic elements can vanish without a trace. Venus's clouds hold a secret ingredient, something dark, elusive, and utterly perplexing. When scientists peer at the planet in ultraviolet light, vast patches of its atmosphere appear to swallow the light whole, leaving behind bizarre, shifting patterns of absorption no known substance can fully explain. These mysterious UV absorbers drift through the upper cloud decks, painting the planet with strange, ephemeral stains that appear, vanish, and reform with no discernible rhythm. Whatever this material is, it doesn't behave like anything in our terrestrial catalogue of chemistry, and it's hiding in plain sight, camouflaged within the very clouds we've studied for decades. The hunt for the absorber's identity reads like a cosmic whodunit. Early suspects included sulfur in various forms. After all, Venus's atmosphere is practically drowning in sulfur compounds. Sulfur dioxide, sulfuric acid, even exotic allotropes like sulfur polymers could theoretically latch onto UV light. Some lab experiments showed promise, with certain sulfur chains producing absorption bands close to what's observed. But here's the catch: no sulfur compound matches the full spectral fingerprint. The real absorber is pickier, absorbing specific UV wavelengths with surgical precision while ignoring others. A quirk no sulfur variant replicates perfectly. Then there's the chlorine angle. Venus's atmosphere hosts trace amounts of chlorine gas, and when exposed to sunlight, it can form compounds like chlorine dioxide, a molecule notorious on Earth for its ability to rip apart organic matter. Could this be the UV thief? Possibly, but the math doesn't quite add up. Chlorine compounds tend to be unstable under Venusian conditions, breaking apart too quickly to account for the absorber's persistence. Unless, of course, something is continuously replenishing them, like hidden volcanic vents spewing fresh chlorine into the clouds. The plot thickens when you consider the absorber's bizarre behavior. Unlike passive chemicals, this stuff seems to cluster and disperse almost intentionally, forming continent-sized blotches that morph over days or weeks. Some researchers float the idea of ferric chloride, an iron-chlorine compound that could, in theory, form tiny suspended particles with just the right light-absorbing properties. But Venus's surface is notoriously poor in iron, making this explanation a stretch. Others wonder if the answer lies in something entirely new, a Venus-exclusive compound forged in the planet's unique pressure cooker of heat, acid, and sunlight. The darkest twist: this might not be a single substance at all. The spectral data could be a mosaic, the combined signature of multiple chemicals interacting in ways we've never seen. Picture a dynamic dance of sulfur, chlorine, and maybe even carbon-based molecules, constantly reacting and reforming under the UV spotlight. Or worse, what if the absorber isn't a chemical at all, but a physical phenomenon? Some theorists suggest clouds of nanometer-scale particles, their size and shape tuned to swallow specific wavelengths, like a cosmic version of stained glass. What makes this enigma so urgent isn't just the academic puzzle. If the absorber is a new form of sulfur, it could rewrite our understanding of atmospheric chemistry. If it's chlorine-based, it might hint at unseen volcanic activity, and if it's something else entirely, well, that could mean we've been overlooking a fundamental piece of planetary science. Every mission to Venus trains its instruments on these dark stains, searching for the spectral smoking gun. Until we find it, the absorber remains a ghost in the machine, a shadowy player in Venus's toxic drama, hiding in the light it steals. Rising like shattered fortresses from Venus's scorched plains, the tesserae stand as some of the most alien landscapes in our solar system, vast, fractured plateaus crisscrossed with grooves and ridges in chaotic patterns that defy earthly geology. These elevated regions, some spanning areas larger than Texas, look like giant puzzle pieces forced together by a careless hand. their edges warped and folded in ways that suggest either tectonic violence or some unimaginable volcanic tantrum. What makes them truly baffling isn't just their appearance, it's that they might be the last remnants of Venus's ancient skin, a fossilized record of a time when the planet wasn't so hellish. The Tesserae's most striking feature is their texture. Radar maps from missions like Magellan reveal surfaces so intricately deformed they resemble crumpled tinfoil, with intersecting fractures forming geometric grids unlike anything on Earth. Some sections tilt at sharp angles, as if entire slabs of crust were shoved upward by subterranean forces. Others show telltale signs of compression, parallel ridges stacked like pleated fabric, hinting at colossal pressures that squeeze the landscape like an accordion. If these features formed on Earth, we'd blame plate tectonics, but Venus has no moving plates, at least none we've detected. So what could have mangled its crust so violently? One camp argues for a long-dead tectonic regime. Perhaps early Venus did have plate tectonics, which ground to a halt as the planet's crust thickened and its water vanished, leaving these crumpled highlands as tombstones to that lost system. In this scenario, the Tesserae would be Venus's version of Earth's oldest continents, battered relics of a more dynamic past. But skeptics point out a glaring flaw. The Tesserae lack the mineral diversity seen in Earth's continental crust. Without granite or other lightweight rocks typical of continents, could these really be analogues? The alternative theory is far more unsettling, that the Tesserae were forged not by tectonics but by lava itself. Venus's surface is littered with evidence of catastrophic volcanism, and some researchers propose that these plateaus might be the result of lava blisters, colossal domes of molten rock that pushed upward, then collapsed under their own weight, leaving behind a cracked, jumbled mess. Imagine syrup boiling in a pan, forming thick skins that fold and fracture as bubbles burst beneath them. If true, the Tesserae wouldn't be continents at all, but the scars of a planet-wide meltdown. Yet even this explanation falters when faced with the Tesserae's staggering diversity. Some regions show crisp, angular fractures suggestive of brittle crust snapping under stress. Others appear softened, almost melted at the edges, as if heat played a role in their deformation. Then there's the mystery of their elevation. Why do these plateaus stand so high? On Earth, mountains rise through collisions or volcanic buildup, but Venus's Tesserae seem to float above the surrounding plains like ghostly islands, their bases not rooted in any obvious geological process. The darkest enigma lies in their age. If the Tesserae are ancient, they could hold clues to Venus's lost oceans or early magnetic field. But some radar data suggests they might be surprisingly young, their sharp edges uneroded by the planet's corrosive winds. Could they still be forming today, creaking and splitting under stresses we don't yet understand? Or are we seeing the last gasps of a geological engine that's nearly spent? Every theory raises more questions. Why do Tesserae cluster in certain regions but avoid others? What explains their eerie similarity to some icy terrains on Jupiter's moon Europa, a world with no volcanoes at all? Until we land a rover on these fractured highlands, drilling into their twisted layers, the Tesserae will remain a planetary Rorschach test. Scientists see in them what their expertise predisposes them to see: tectonic ghosts, volcanic ruins, or something else entirely. One thing's certain, these aren't just random wrinkles, they're a cipher etched in stone and waiting to be read. Venus's clouds aren't just fast, they're capable of something even stranger: sudden, unexplained standstills. Imagine a planetary-scale traffic jam, where winds that typically scream at hurricane speeds grind to a halt for hours or even days, freezing vast stretches of the atmosphere in place. These eerie pauses aren't random. They cluster in specific regions like atmospheric gridlock, with cloud layers locking into immobility as if hitting an invisible wall. For scientists, these halts aren't just oddities, they're glaring red flags that Venus's atmosphere operates by rules we've yet to crack. The most dramatic examples occur near the planet's equator, where orbital observations have caught entire cloud decks, some spanning thousands of miles, abruptly slamming the brakes. Infrared imagery reveals the aftermath: temperature gradients flatlining, wind shear vanishing, and turbulent eddies dissolving into unnatural calm. It's as if someone flipped a switch, turning off the machinery that drives Venus's superrotating winds. The strangest part, these pauses don't correlate with solar activity, volcanic eruptions, or any other obvious trigger. They happen when they please, defying prediction. One leading theory points to atmospheric waves, not the gentle ripples we know on Earth, but planet-scale oscillations generated when Venus's supersonic winds collide with mountain ranges or other obstacles. These waves might propagate upward, interfering destructively to create dead zones where momentum cancels out. Picture ocean waves crashing into each other, momentarily stilling the water's surface. But here's the problem. Computer models suggest these waves should dissipate long before achieving such dramatic braking effects. The energy required to stall Venus's winds, even temporarily, exceeds anything these waves should logically muster. Then there's the thermal inertia hypothesis. Venus's day side broils under relentless solar radiation, while its night side plunges into frigid darkness. This extreme Chinese letter cold theoretically create pockets where atmospheric layers decouple, their heat differentials neutralizing wind shear. But if that's the case, why do the pauses occur in narrow bands rather than across entire hemispheres? And why don't similar gas giants with even wilder temperature swings exhibit this behavior? The darkest wild card, electromagnetism. Venus's upper atmosphere buzzes with charged particles, and some researchers speculate that solar-wind interactions might sporadically induce electric currents capable of gluing clouds in place. It's a stretch, but so is every other explanation. Until we send probes to orbit during one of these events, measuring every fluctuation in real time, the truth will remain as elusive as the winds themselves. What makes these pauses so unsettling isn't just their defiance of physics, it's their implication that Venus's atmosphere isn't just fast or chaotic. It's unfinished, a system still rewriting its own rules in real time. And every time those clouds grind to a halt, they're sending us a message. This world is playing a game we don't yet know how to win. Every planet in the inner solar system started with the same basic ingredients, so why does Venus's atmosphere look like it's missing a key piece of the recipe? Hydrogen, the lightest and most abundant element in the universe, should be floating around Venus in detectable amounts, just as it does on Earth and Mars. Instead, something stripped it away, leaving behind a haunting chemical discrepancy that rewrites the story of how planets lose their water and perhaps their chances at life. Take deuterium, hydrogen's heavier isotope. On Earth, for every million hydrogen atoms in our oceans, about 150 are deuterium, a rare but stable ratio. Mars, despite its thin atmosphere, shows a similar signature, just slightly enriched due to solar wind erosion over billions of years. But Venus, its deuterium levels are explosively high, clocking in at 150 times the concentration found on Earth. This isn't just a subtle difference, it's a screaming anomaly, a neon sign pointing to a violent, water-starved past. The textbook explanation is simple. Venus lost its water, and the physics behind that loss favored lightweight hydrogen. Picture a planet once rich with oceans, its water molecules broken apart by solar radiation. The hydrogen atoms, light and nimble, escaped into space more easily, while the heavier deuterium lagged behind, accumulating like residue in an evaporating dish. Over time, the atmosphere's deuterium ratio skyrocketed, a textbook case of atmospheric escape. Except the numbers don't add up. If Venus started with Earth-like oceans, the current deuterium excess implies it should have lost an ocean's worth of water dozens of times over. The sheer volume required strange plausibility, unless the planet was once drenched on a scale we've never imagined. Some researchers argue for a primordial Venus drowning in supercritical water vapor, a global pressure cooker where deuterium production outpaced hydrogen loss. Others propose an even darker scenario, that Venus's water didn't just evaporate, it was chemically cannibalized. Here's where the plot twists. Sulfuric acid, the dominant compound in Venus's clouds, is a notorious hydrogen thief. Under the planet's extreme conditions, it could have reacted with water vapor, locking hydrogen into unrecoverable compounds while letting deuterium build up in the atmosphere. Imagine a planetary-scale chemistry experiment where water didn't just vanish, it was dismantled and repurposed, its hydrogen atoms imprisoned in minerals or acid droplets. Yet even this theory falters when faced with the isotopic ratios of other elements. Oxygen, water's other half, shows no matching enrichment. If hydrogen was stripped away, where did all the oxygen go? Some speculate it bonded with carbon to form the planet's thick carbon dioxide shroud. Others wonder if Venus's crust, baked and oxidized over eons, absorbed it like a sponge, though no rover has ever confirmed those subterranean reservoirs. The most unsettling possibility: we're seeing the aftermath of a cosmic heist where Venus's water was stolen not just by solar winds or chemistry, but by its own geology. Recent models suggest that early volcanic eruptions, more violent than anything in Earth's history, might have blasted water molecules apart, scattering their components beyond recovery. If true, Venus didn't just lose its water, it burned it away, turning oceans into atmospheric fuel for its own destruction. Every probe that analyzes Venus's deuterium adds another piece to this puzzle, but none have found the smoking gun. Until we sample its rocks directly or map its hidden water relics, the Great Venusian Drought remains a cautionary tale, a reminder that planets, like people, can wither from the inside out. And the isotopes left behind, they're not just clues, they're scars. Among Venus's many geological oddities, some of the most unsettling are its ghost craters, impact sites that appear half erased, their outlines blurred as if someone dragged a cosmic eraser across the surface. These pale imprints dot the landscape, their rims softened and floors suspiciously flat, standing in stark contrast to the sharp, bowl-shaped craters we see on the Moon or Mercury. What makes them truly baffling isn't just their faded appearance, it's how they coexist with perfectly preserved neighbors, as if some invisible force is selectively sanding away the planet's scars while leaving others untouched. The obvious suspect is lava. Venus's volcanic past is written across its surface in mile-high mountains and sprawling plains of hardened basalt. When magma floods a crater, it can fill the depression like molten wax in a mold, leaving behind a smooth, featureless plain where the original impact once stood. Some ghost craters support this theory. Their floors mirror the surrounding terrain, suggesting they were indeed buried by later eruptions. But here's the catch: many of these faded scars sit far from obvious lava sources, in regions where radar shows no evidence of recent flows. If lava isn't the artist behind these erasures, what is? One radical idea points to the planet's crushing atmosphere. With surface pressures 90 times Earth's, Venus's air behaves more like a slow-moving fluid than a gas. Over millennia, corrosive winds laden with sulfuric acid might sandblast crater rims, wearing them down grain by grain while depositing mineral residues in the basins. Picture a desert canyon eroded by wind, but on a planetary scale, a process so gradual it could take millions of years to soften a single crater. Yet this doesn't explain why some craters resist the erosion entirely, their sharp edges defying the same forces that erase others just miles away. Then there's the subsurface angle. Venus's crust, lacking Earth's tectonic renewal, might be more plastic than we realize. Under extreme heat and pressure, the ground could slowly sag, causing older craters to slump inward like aging soufflés. Thermal scans reveal that some ghost craters sit above unusually warm regions, hinting at hidden magma pockets that might be softening the rock from below. But if this is true, why don't all craters in these zones show the same distortion? The selectivity is maddening, as if Venus has a secret criteria for which scars it allows to fade. The darkest twist comes from the crater clusters themselves. In certain regions, ghost craters outnumber fresh ones, forming eerie graveyards of half-remembered impact. But in others, like the Meade Crater Basin, one of Venus's largest and best-preserved impact sites, the scars remain crisp, their walls towering over untouched plains. This disparity suggests the planet's resurfacing wasn't just a uniform process. Something, whether lava, weather, or something we haven't imagined, acted in patches, erasing history piecemeal. The implications stretch beyond geology. If we can't explain why some craters vanish and others endure, how can we trust Venus's surface to tell us its true age? Are the ghost craters evidence of a planet still geologically active, quietly editing its past? Or are they tombstones for a lost era, when Venus's crust behaved in ways no model predicts? Until we touch down on those haunted plains, the ghosts will keep their secrets, whispering of forces we've yet to name, on a world that refuses to sit still. Venus doesn't just lose water and hydrogen. It bleeds oxygen into space, ripped away by an invisible force more powerful than anything Earth can muster. Scientists call it the electric wind, a relentless atmospheric current fueled by the planet's own electric field, accelerating oxygen ions to escape velocity like a cosmic slingshot. While Earth has a gentle polar wind that nudges particles into space, Venus's version is a full-blown exodus, 5 times stronger, with no clear explanation for its ferocity. This isn't just solar wind at work. Charged particles from the Sun play a role, but Venus's electric field is something else entirely. A planetary-scale voltage generated by the interaction of sunlight and the upper atmosphere's ionized particles. Imagine the entire sky acting like a giant battery, its positive and negative charges separating to create a vertical current so potent it overrides gravity's grip on oxygen. On Earth, our magnetic field shields us from the worst of this effect, but Venus, defenseless, lets the electric wind run wild. The result, a steady hemorrhage of oxygen ions, fleeing into space at a rate that would drain an Earth-sized ocean in just a few 100 million years. The mystery lies in the wind's strength. Venus's electric field clocks in at around 10 volts per meter, dwarfing Earth's paltry 2. Conventional models suggest sunlight alone shouldn't generate this much voltage, so what's juicing the system? One theory points to the planet's suffocating carbon dioxide atmosphere. When ultraviolet light breaks apart CO2 molecules, it creates a surplus of free electrons, supercharging the ionosphere. But even this falls short of explaining the electric wind's brute force. Some researchers suspect Venus's lack of a magnetic field allows solar wind to penetrate deeper, amplifying the effect like a live wire touching water. Others wonder if the planet's extreme greenhouse effect plays a role, trapping heat in a way that stirs the ionosphere into a frenzy. The darkest clue comes from the oxygen itself. Unlike hydrogen, oxygen is heavy, 23 times heavier than its cosmic counterpart. For Venus's electric wind to hurl these bulky ions into space, the field must be unimaginably efficient, a particle accelerator built into the sky. Yet no known atmospheric process on any other planet operates at this scale. Even Mars, with its thin air and weak magnetism, can't muster such a violent exodus. What makes this enigma so urgent is what it implies for Venus's past and Earth's future. If the electric wind has been this strong for billions of years, it could explain why Venus's water vanished so completely, its oxygen stripped away molecule by molecule. And if a planet so similar to ours can spawn such a ruthless atmospheric drain, what's stopping Earth from developing one? As our own ionosphere faces growing pressure from climate change and solar variability, Venus stands as a chilling reminder. Sometimes the wind doesn't just blow. It steals. From its backward spin to its vanishing oceans, Venus has spent decades mocking our textbooks, but these 5 mysteries stand out as the most jaw-dropping. First, the planet's superrotating atmosphere, where hurricane-speed winds circle the globe every 4 days while the surface below creeps along at a snail's pace. No model fully explains how the upper clouds accelerate to such impossible velocities without tearing themselves apart. Then there's the phosphine enigma, a gas in the clouds that on Earth signals life. Is it microbes floating in the acid haze or some exotic chemistry we've yet to discover? The debate still rages. Third, the missing craters. Venus's surface looks suspiciously young, as if a planetary-scale lava flood erased its scars 500 million years ago. But why did some regions reset while others retained ancient impacts? The uneven resurfacing hints at geological tantrums we can't yet comprehend. Fourth, the shining mountains' highland ranges glowing in infrared despite being made of cold, ancient rock. Are they laced with fluorescent minerals, or is some hidden energy source baking them from below? But the crown jewel of Venusian weirdness, the dark vortex at its poles, a continent-sized whirlpool of gas that morphs between hourglass and spiral shapes like a living thing. Unlike Earth's orderly polar weather, this maelstrom pulses erratically, sometimes splitting into triple storms before merging back together, a defiance of fluid dynamics that leaves physicists speechless. Every probe we send reveals more questions than answers. Venus doesn't just defy expectations, it rewrites the rules, proving that even in our cosmic backyard, nature holds cards we've never seen. So what's your pick? Which of these enigmas keeps you up at night? Drop your thoughts below, and if you're hungry for more cosmic mysteries, hit subscribe. The universe is stranger than fiction, and we're just getting started.